So welcome back, everyone, for the 10th lecture of my 16-lecture course. So we're going to finish talking about the law of large numbers for the largest component in our differential random graphs today, and then on Thursday we'll start to use the information we've developed to understand minimum spanning trees of random graphs. So let me remind you where we were at. I know there's a fair amount of notation, but I'll try to keep things as clean as I can today. And we don't have a ton left to do, so you know, we'll take it easy. Feel free to interrupt with questions if things are unclear, and I'll try to make everything as clear as I can. So remember, we were in the midst of analyzing the depth first Q process for G and P in order to prove this weak law of large numbers. So the sort of key insight was that this process X, which was tracking the number of active vertices, number of newly discovered vertices minus 1, hits new running minima each time it finishes discovering a component. So we did this example of an exploration of graph with these 4 connected components. And then our goal was going to be to show, so if we sort of now, rather than looking at a small example, we imagine looking at a large graph, so n very large, and we kind of zoom out in this picture, then you know, our hope is to see, or what we're in the process of showing, is that this process S on a large scale will closely track some deterministic curve, which we called F, right? So that's our goal, was to show that S closely tracks F, and then to use that to show that the component explored between these particular times R and L, or I guess it was L and R, L being the left time and R being the right time, has size basically n theta of lambda. Okay, so so I'm going to carry along all the, you know, large number of parameters and terminology that I'm using on the right, just because I had the feeling it was a little bit overwhelming trying to keep track of all of this last lecture. You know, there's maybe I hope there's less of it than it looks like even on the slides, but let's just go through the slides, go through this list, even though it's going to be carried along, just to make sure it's sort of still in everyone's mind. So P was our percolation parameter. We wrote it as lambda over n, or 1 plus epsilon over n, and we had some absolute constant bound A on the numerator there. And also we needed P to be at least this much bigger than 1. So epsilon n to the third should tend to infinity. Then we'd written D for n theta of lambda. This is the point where this curve n minus t minus n e to the minus pt, so let me make that green to agree with my notation. This is the spot where that curve returns to 0. And in my previous lectures I was drawing, I'd drawn the difference between n minus p and n e to the minus pt. So we had a drawing like this, right? And so now I've just drawn the actual curve rather than the line and the difference. Okay. So then we know that each time the exploration process sort of hits a new local minimum, that means it finishes exploring a component. So we had fixed this sort of early time G, and we were going to look at the component straddling time G. So G was omega root n over epsilon, and the sort of key fact about that was that it was much smaller than n to the 2/3, and in particular smaller than epsilon n. So then we'd define, so this was the time L. It was sort of the last time we hit a running minimum before time G, and then time R will be the first time after that we drop below level L. Okay, so this depth here was Z, and so we finish exploring that component, which is alive, being explored at time G, when the process S over here hits minus Z minus 1. Okay, so S of R is minus Z minus 1. Okay, so that's the sort of picture of where we're at. And now last lecture, we already showed bounds on how closely S tracks F. So let me remind you of those. So last lecture, we saw that for all t, the difference between Si and Fi up to time t was so stochastically bounded by the sum of two errors. So one was the difference between Si and some auxiliary process S tilde, which more closely resembled a martingale, and then the other was the difference between S tilde and F. Okay, and then we bounded each of these in turn. So we deterministically had that this difference was at most pt kappa of t, kappa being the number of components we see up to time t, and this difference being order root t in probability. Okay, so that so that in sum, this is for all t at most n, so we could use that pt is at most Pn, which is at most A, to rewrite this bound as at most A kappa T plus order root T in probability. Okay, and so our goal is to use this to prove that R divided by n theta lambda converges in probability to 1. Right, and this was, so proving that R over n theta lambda converges to 1 also yields R minus L over n theta lambda converges to 1, because L is bounded by G, which is a lower order term. Okay, so is that story, is everyone comfortable with that story? I was disappointed that no one had their cameras on, and then I realized I just didn't have it on gallery view, so I'm glad to see some of you. Okay, that feels a little more like a class now. Right, so so let me prove this. I know that S is closely tracking F, so if I'm going to use that to prove that to prove something about when when S hits this local minimum, I'm going to need some information about F. So let me just tell you the information I'm going to use about F, and then sort of, which basically I'm going to get that information just by taking derivatives of F and doing some simple computations. So let me just state the proposition and then use it to finish with our goal, and then I'll return to proving the proposition at the end. Okay, so here's what we want to know, or here's what we're going to use about F. So for n large, so F of t is at least, so is much bigger than root d. Right? This is d down here. I'm sorry I have two notations for it, but I wanted when I was drawing it on this picture, having gauche and droite left and right made sense to me, but d is the same as n theta lambda. So d is our denominator here as well. D denominator, that's good. So this is d, right? So so when n is large, F is much bigger than root d for for t between g and d minus g. Okay, and on the other hand, by time d plus g, f has dropped to much smaller than minus root t. And remember, omega is some function of n, which is tending to infinity. Okay, so so that's saying in this picture, right, that we control, you know, this this gap here. This is much bigger than well, what did I write? Bigger than 10 root omega d, and that's true all the way up to the time d minus g, which in my drawing, this d minus g and g look big, right? But really this gap here is small compared with the total length of the interval. And on the other hand, you know, by the time d plus g over here, we're at this sort of the same negative distance away from this line. Okay, so that's what I want to use to prove the law of large numbers. And let me first just use it to prove a bound on z. You see, z is gonna factor into this error bound here, because we're gonna you know, one of the terms in our upper bound is the number of components explored, and we'll use that at this time g. So to control this term, we need to understand how big z is, and we can get control on z just from using this proposition. Okay, so I'll state it as a corollary. So z is little o of root d in probability. Okay, which means that, you know, for any alpha greater than 0, the probability that z over root d is bigger than alpha tends to 0 as n tends to infinity. Okay. So the proof of this isn't hard. So we know that at time L, the process, this is the that's here, right? That's when the process hits its last local minima before time g, and we called that local minimum, you know, that gap size z. So at time L, the process is just at minus z. Okay, so I mean, a bit more formally, SL is the same as S of tz, which we know is ATZ minus kappa tz. We proved that identity in, I think, the second error training lecture. But at the time when we finish exploring a component, the active set is empty, and so we just get minus tz. So that's minus z. Okay, so that's the first fact. And now this is the only. Now I'm going to use this bound on S tilde. So this is the last time that S tilde is going to feature in the lecture. Okay, that's why I didn't remind you of the definition. I'm going to use that we proved this stochastic bound on the difference between S tilde and F, but after that S tilde will go away. We won't need it anymore. Okay, so we know that so S minus S tilde is at most PL kappa L, and so that's PL Z, and now L is random, but it's at most G, right? It was because it was the last time we finished exploring a component before G, so that's at most PGZ. And now G is little o of n, right? And P is order 1 over n. So this term PG here is little o 1. So this whole thing is little o z. Okay, so that says that up to this time L, the error between S and S tilde is little o of z. Okay, and so that means that well, SL is minus z, SL tilde is little o of z, and so that means that at least when n is large, SL tilde is at most is less than, say, negative half z, so minus z over 2. Okay, but we also know that f of L is positive, right? Because L is less than G, which is much less than D, and D was the first time after time 0 that f becomes negative. Okay, so that tells us that so z over 2 is at most the difference between s tilde and f. Okay, and we can bound that. This time L is random, but we can bound that from above by the largest time before time g, the largest difference between s tilde and f before time g. Okay, just because L is at most g. Right, so this is because I have here, oh, sorry, I'm missing an inequality. This is less than minus z over 2. Right, so I'm just saying, because this is positive, here I'm going to get something less than minus z over 2 in absolute value before I taking up less than minus z over 2. So after taking absolute values, I get something bigger than z over 2. And now what bound do I have on the right? Well, we said that difference is order root g in probability. Okay, but g is little o of epsilon n, right? And d is on the order of epsilon n, and so this is little o of root d in probability. Okay, and that was precisely our goal, was to say that of this corollary, was to say that z is little o of root d. Okay, so that was just a matter of combining the fact that f is positive with the bounds we have on the differences between s and s tilde and s tilde and f, to say that we haven't seen too many components before time g. Okay, so that's the first step, and now I want to derive one more bound, which is basically to say, you know, this bound here. So this kappa t, this bound looks a lot better when t is small, because that's when we have control over, you know, well, potentially have better control over the number of components explored. But on the other hand, between times L and R, kappa doesn't change, right? We're in the midst of exploring a single component. So that means that in principle, we can extend our good control over, over this error a lot further into the future, as long as we know that, that the process hasn't started hitting new local minima. Okay, so I want to use that now. So we're going to use the bound. So we have the. Let me write it out again, because I didn't copy this down on the right. So we know that this error is at most a kappa t plus order root t in probability, but also we know that kappa r is just z plus 1. We finished exploring our z plus first component at time r, which is now, we know that's little o of root d. Okay, so that tells us that that if we're willing to stop looking, so if we take t to be the minimum of time d plus g and this time r when we finish exploring that component, then at that time the bound a kappa t is just a is at most a z plus 1, so we get a little o root d from the first term, and then a big O root. This is our time t, right? So that's at most root of d plus g, and now g is a smaller order correction to d, right? We already used that once. D is on the order epsilon n, and g is little o of epsilon n. So this whole thing is just so this square root d plus g just looks like square root d, and that tells us that this whole error now is order root d. Okay. So this is good news, because we've taken a bound which had one part which was a random variable, and we've managed to write it just as a stochastic bound on this maximum error, basically up to the time we're interested in, up to the time we finish exploring the component in question. Okay, so let's now put that together to show that that this component that we're exploring with high probability really will, finish its exploration right around time d. So specifically we'll show that it's going to finish with high probability. The exploration will finish between time d minus g and d plus g. Okay, so let me create a good event that will have probability tending to 1, and that on that event we'll see that that R is going to lie between d minus g and d plus g. Okay, so the event is just that this maximum error up to time minimum of d plus g and R, Si minus Fi, is at most square root omega d. Okay, so that's my good event, right? And then the bound we just proved here, that this maximum error is order root d, immediately says that the probability of E tends to 1. Okay, and now we're going to show that when E occurs, and also Z is at most root d, then R will fall in the interval d minus g, d plus g. Okay, and this so this whole interval here is d minus little o of d, d plus little o of d, and d is n theta lambda, right? So this is this really shows that R is 1 plus little o1 n theta lambda when these events occur. Okay, so the probability of E tends to 1, and the probability that Z is at most root d tends to 1, because we saw that Z is little o of root d in probability. Okay, so so the two events I've written in black here both have probability tending to 1. So this this proves that R over d, which is R over n theta, converges in probability to 1. And so it just remains to prove that that on the event that that E occurs and Z is at most root d, we indeed have R in this interval. Okay, is that logic clear? I haven't been monitoring the chat. D greater than G suffices. That was a few minutes ago. Okay. Right. So let's prove that let's prove that when these events occur, we indeed, first return to a new local minimum in this interval. Okay, so we know that f of t is at least 10 root omega d. This is, well, to be proved, right? But I sort of postponed the analysis of f till the end. So we know that this holds, for t between g and d minus g. So that means that when e occurs, we will have, s of I is at least 9 root omega d, right? Because the error is at most root omega d, and f is bigger than that, 10 times bigger than that. And in particular is positive for t in this interval g d minus g, right? But at time r, s is minus z minus 1. In particular, it's negative, right? And r doesn't occur. R is after time g, because the time L was the last time before g that we hit a new local minimum, right? So r is after g, and so if s is positive between g and d minus g, then r can't be between g and d minus g. Okay, and so that means that so r, right, which is the minimum t bigger than g, such that st is less than minus z is another way to write it. That must be bigger than d minus g. Okay, so that's one of the two things we wanted. We wanted that when e occurs and z is at most root d, then r lives in this interval. We've shown that it's bigger than the left endpoint of the interval. Okay, and actually for that we only needed e to occur, but for the other bound we'll use both. Okay, so when e occurs and z is at most root d, then we'll just show that at time d plus g, s has gotten small enough that it must have passed this minus z minus 1, right? So we know that it's at most, the error bound we get from e when e occurs is a root omega d. So at most f of d plus g plus root omega d. Okay, and now this, so this term, this is to be proved, but we said was less than minus 10 root omega d. So this whole thing is less than minus 9 root omega d, which is less than minus z. Okay, because z is at most root d, and this is something tending to infinity relative to root d. Okay, and so that means that r is less than d plus g. Okay, so that proves. So this completes. So this shows the law of large numbers, r over n theta, tending to 1, sort of up to the claims about f. So so let me turn to those, and I think I should probably, I mean, I've kind of restated them in the course of the proof, but I think I'll copy the proposition down just so we have it stated explicitly before I go into that proof. But any questions about the structure of the proof before we do that? So really, up to all the technical details, and there were a fair number, what the proof really boiled down to was just getting good control on the error between s and this process f, which it approximately tracks. Okay. So for those for those who were in, well, maybe I'll say a word after we prove this proposition about which will be relevant to Kavita Ramanan's talk today, because she mentioned a couple things about Erish-Renyi random graphs, which I haven't explicitly stated, but which are sort of easy to make as side remarks now. Okay, so we're, did I not copy? We're trying to prove these bounds on F. Okay, so that's what it remains to show. So, you know, we have some information about F already. We know that. So this is the definition of F: n minus t minus n e to the minus pt. We know that f of d is 0. That's just by you know, plugging in n. If you plug in d, which is n theta of lambda, you precisely see the Poisson, the identity for the Poisson survival probability that we've used before come out. So those I won't reprove. But to start to get these bounds, I want to you know, just compute the first two derivatives of f and then write down some simple inequalities. So so what's f prime of t? That's so minus 1 plus np e to the minus pt. Okay, remember f is over here. And I can rewrite that if I like as minus 1 plus p and then n minus t minus f of t. So I've just used that n minus t minus f of t is n e to the minus pt. Okay. And now that gives, the reason I want to write things that way is because then if I look at the derivative evaluated at d, I get minus 1 plus p n minus d minus f of d, but f of d is 0. So that's just minus 1 plus p times n minus d, and now d is n theta of lambda. Okay, so so if I you know, if I so if I've just canceled that and used the definition of d, and now np is lambda, right? So I have lambda and then lambda theta of lambda here. So this is minus 1 plus lambda times 1 minus theta lambda. Well, that was that's the definition of the dual parameter lambda hat, right? So that's minus 1 plus lambda hat, where so the dual parameter for a Poisson-Binomial tree with parameter lambda. Okay, and now for the second derivative, I just have that this is minus, so np squared e to the minus pt. So in particular, so it's negative, so f is concave, and I also have an absolute lower bound on this because p is at most a over n. Okay, and so and the e to the minus pt is at most 1, so I can just absolutely bound this from below by minus a squared over n. Okay, so it's concave, but I have some bound on the concavity. Okay, so if I combine those, that tells me that you know, I'll start by getting a lower bound on f prime at time t. So that's at least f prime of 0 minus t times a squared on 2, right? This is just looking at how quickly the first derivative is changing using the second derivative. Okay. Well, what's f prime at 0 is np minus 1, right? Because this at t is 0, the e to the minus pt just gives me 1. So that's np minus 1 minus t a squared over 2, which I could write as oh, sorry, that 2 should be an n, right? Yeah, because np squared is n times lambda squared over n squared, which is at most a over n. Yeah, so these, sorry about that, those 2's should be n's. I mean, it's true with 2, but I think I need it to be an n. So Right. And now NP is lambda, right? And lambda is 1 plus epsilon. So this NP minus 1 is just epsilon. So this whole thing we get is epsilon minus TA squared on n. Okay. And so as long as this correction here is, say, at most epsilon over 2, then we can say the derivative of f is bigger than epsilon over 2, and then use that to get a lower bound on f. Okay, so that tells us that f of t, let's say f prime of t is at least epsilon over 2 for t at most epsilon n on 2a squared. Okay, and so that means that if t is less than g, okay, well, g is, so we have a lower bound on the derivative of f that's valid up to this something of order epsilon n, right? Because a is a constant. But we said g was little o of epsilon n. Okay, so that means our lower bound on the derivative of f is valid all the way up to g. Okay, so so g is less than epsilon n over 2a squared, at least for n large. Okay, so that gives, so for t like that, f of t is at least f of 0 plus, so derivative epsilon over 2 for time t, epsilon t over 2. And f of 0 is just 0, right? So then we have n minus 0 minus n. Okay, so this is a lower bound of epsilon at t over 2 for t at most g. And so in particular, let's apply that at time g. At time g, that tells us that f of g is at least epsilon g over 2. Okay, and now epsilon, so let's just plug in the definition of g here, omega root n over epsilon. That gives us omega over 2 root epsilon n. And now epsilon n is of the same order as d. So that's like up to constants the same as omega root d. And all we wanted was that it was at least 10 root omega d, right? So that's actually much bigger than root omega d. And in particular, it's bigger than 10 root omega d for n large. Okay, so that's one of the bounds we wanted. It really just comes from studying the derivatives of f. Okay, and now for the other bounds, we're going to again study sort of the rate of change of f, but around d rather than around 0. Okay, so so that'll take us just another 5 minutes, and then we'll be done with this topic. So we know that f prime at d is the dual parameter lambda hat minus 1. And we saw in previous lectures, or I stated, I actually left it as an exercise, but that this is, so lambda hat is on the order of 1 minus epsilon, up to constants. So lambda hat minus 1 is on the order of minus epsilon. Okay, and so that tells us that if we look at, say, s between 0 and g, so I'm going to look at what the derivative of f is like near d. Okay, well, again, I have, so let me, maybe it's worth scrolling back to the picture of f for a second. Okay, I'm trying to prove right now that I'm trying to get a bound on this height here. Okay, and the reason I have to be a little bit careful is because f is concave, which means that it's bending downwards as I go to the left, right? I can't just use the slope, but it's bending downwards. So any bound I prove on the left, I'll get, I'll do better on the right. So if I can prove that this distance, that this is at least 10 root omega d over here, then I'll sort of instantly be able to conclude that I have at least height 10 root d, the same distance over on the right, because here we're bending away from the line and here we're bending toward the line. Okay, so I'm just going to control sort of how much the slope decreases by time d minus g to prove the height bound that we want. So what's the slope of f at time d minus s? Well, our bound on the second derivative tells us that that's at most so sa squared over n, right? This is our bound on the second derivative. Okay, so that's at most lambda hat minus 1 plus ga squared on n. And now g is little o of epsilon n, and so g on n is little o of epsilon. So this term is of order epsilon, and this term is little o of epsilon. Okay, and so the whole thing is on the order of minus epsilon. The whole thing is on the order of minus epsilon. Okay, and so that tells me that making this quantitative, I'm using this asymptotic notation meaning up to constants. That tells me that there's some positive alpha such that f of d minus g is at least, so f of d plus alpha epsilon g. Okay, and so just using the definition, so f of d is 0, and g is written over here. So when I multiply by epsilon, I get so alpha omega root epsilon n, and again, so this is of order d, and so this whole thing is much bigger than the square root of omega d, and in particular is bigger than 10 root omega d for n large. Okay, so what have we proved now? I'll just say, but by my comments about concavity, it also follows that f of d plus g is less than minus 10 root omega d. Okay, so that's I won't say more about that. But so let's look at the information we have now and what we were trying to prove. We wanted to know that f stays large between times g and d minus g, and then it gets negative and large by time d plus g. Okay. Well, we've proved that f is large at time g, and that it is large at time d minus g, and that it is large and negative at time d plus g, right? But we also know that f is concave. So if it's large at time g and it's large at time d minus g, then it's immediately large at all the intermediate times. Okay, so there's not actually anything additional to prove there. Okay, so since that's the last observation. So since f is concave, follows that so f of t is bigger than 10 root omega d for all t in this interval, g d minus d, d minus g. Okay. So I see a comment in the chat. That looks like I maybe missed it. Sorry about that. Right. So that's that wraps up the long and at times a bit painful proof of the law of large numbers for the largest component. It seems like everyone has frozen. Am I coming through okay?
Yes.
Great, thanks. Good. So I'd like to spend a little bit of time talking about what happens for critical Arashani random graphs now. So this is going to be sort of fairly mathematically careful, but also I'm not going to prove things. I'm going to give sort of relatively detailed heuristics, which I think, given how much we've already seen about these exploration processes, should be quite plausible. And there's sort of a theorem I'll state for which the martingale functional central limit theorem is really needed. So you need to know, in order to make everything perfectly rigorous, how to show that martingales converge to Brownian motion. And I won't go into that, but I think we have enough of the background that the story should feel fairly clear now. So that's sort of what I'll do with the rest of today's lecture, is talk about the critical case. So by which I mean P is 1 over n plus C over n to the 4/3 for C constant. Right, so let me, before we get there, let me remind you, we've now seen that for, so for P of the form, so when P minus 1 over n is much less than negative 1 on n to the 4/3, not 43, we've seen that the size of the largest component is little o of n to the 2/3 in probability. And when P is minus 1 over n is much bigger than 1 on n to the 4/3, we've seen that, so the size of the largest component is basically n times theta of np, and the size of the second largest component, so for all C, so if I look at the, let's say, maximum size of a component, which is not the largest component, that's also little o of n to the 2/3 in probability, right? So we sort of saw this this in two pieces. We saw, before time G, we couldn't explore any large components because G itself wasn't large, and after time D, what was left of the graph looked subcritical enough, so it effectively looked like this subcritical case, which made all the components small. Okay, and so now we're really, so in some sense, zooming in on the only case we don't fully understand, which is when P minus 1 over n is order n to the 4/3. Okay, and so I'd like to, develop our intuition for this by writing down what S of t is again. So this was the sum of x of I for I from 1 to t, which I can also write as the sum from 1 to t of, so it's a binomial, and I want to write that binomial now as n minus I minus the size of AI. Okay. Right, this was the remaining unexplored part of the graph. We had to remove the one vertex per step that we explore, and then the other active vertices. Okay, and now let's use that. Let me use the following sort of heuristic, which, so I'm not going to I'm not going to justify, but it's effectively contained in what we've already proved. So if I look at this sum of the binomial parameters, okay, well, the first term is just nt, okay, and then I have a sum of I for I from 1 to t, so that's minus like t plus 1 choose 2, and then I have the sum of ai. Okay, well, we know that these ai are of order root t. Okay, and so summing that, or rather of order root I, but even the maximum is order root t. Okay, so the sum of those will be sort of at most order t to the 3/2 in probability. Okay, so that is to say, to at least to a first approximation, it looks like we could probably, the dominant contribution to this sum will come from the first two terms in this expression. Okay, so let's think about what that says about the fluctuations of S, okay? Well, you know, if this, let me call this thing star, okay? Then a binomial, right? A sum of binomials looks like another binomial. So, you know, I can think of this whole thing as like a binomial whose parameters are star and p, minus, there's a -1 at each step, right? So I need to subtract t. So what does a binomial like that look like? So that's p is, remember, we're looking at the case p is 1 over n plus c over n to the 4/3. Okay. So so I want to think about that, both the sort of dominant terms and then also the fluctuations of that binomial. Okay, so just by multiplying out this probability by this parameter, we get so we'll get a t term from the nt times 1 over n, and then a ct over n to the 3rd. So now I think I'd like to actually, before I do this computation, sorry, I'd like to focus in on the range of t that I'm interested in. So so I want to take, it'll make the formulas a little bit simpler. So I'm going to take t to be of the form x times n to the 2/3. Okay, so I can justify doing this right away, okay? Because what we sort of already saw in the exploration process was that, you know, after you've been exploring for a while, what's left of the graph starts to look like a subcritical Erdős-Rényi random graph. Okay, and so after you've been exploring for a large constant n to the 2/3 time, if you look at what happens after that time, you'll actually see something that looks like a subcritical graph. Okay, so in particular, you know, if you go on for much longer than time n to the 2/3, you're only going to see components of size little of n to the 2/3. Okay, so really to understand the largest components, it boils down to understanding what happens for the first order n to the 2/3 time, and that's what I want to focus on now. Question in the chat, wait, does the whole sum look like this binomial minus t or the terms? So basically what I'm saying is, you know, a sum of binomials is a binomial, just like a sum of Poissons is a Poisson. So I've extracted the minus t as the sum of the -1s, and then for the sum of binomials, I've effectively just put the sum inside of the first parameter of the binomial. Does that clarify? Great. Okay, so let's use this this value of t in this computation. So so nt times 1 over n is going to give us just a t, which is like x n to the 2/3, and then nt times constant on n to the 4/3 looks like, so we have we get a n to the 5/3 on top and then n to the 4/3 on the bottom. So that'll give us like a constant x. So the constant c from this c over n, x from t, and then n to the 1/3. Okay, and then we should look at this t choose 2. So that's giving us an x squared n to the 4/3, which will kick out a plus. So x squared, or rather minus x squared n to the 3rd. Okay. And then t choose 2, this term is just going to give us a lower order term, right? Because we have x, this t squared is order n to the 4/3, and we're dividing by n to the 4/3. So that's lower order. And everything that comes from this t to the 3/2 is lower order. And then we have fluctuations. So what are the fluctuations of a binomial, right? Fluctuations of binomial NP are of order NP, square root of NP 1 minus P, because the variance is NP 1 minus P. Okay, so the fluctuations of this will be of order in probability. So basically here we have like the dominant term here is NT, and the dominant term here is 1 over N. So that's, so, you know, the multiplying that out, the first order is T, so the fluctuations will be of order T to the half, which is square X to the half N to the third. Okay, so now if we subtract off T, remember this term here is just T, right? X n to the 2/3. So if we remember that our process S looked like this binomial minus T, that's telling us that, so S of T looks something like, so we have, in all of the other terms, we have an n to the third popping out, you see. So we have something like n to the third, and then cx minus x squared on 2. Sorry, I missed the on 2, didn't I? From this, because there was a t squared on 2 coming from here. X squared on 2, and then plus some randomness on the scale x to the half. Okay. And now I'm going to appeal to so there were some questions in the chat. I'm approximating the binomial by its expectation. Well, but then I am keeping track of this additional randomness. And thanks for catching the half. So, you know, there was a question in Jean-Christophe Murat's lecture today about why there was a square root on something. And his answer was effectively, when you have a Gaussian process, the square root is indicating the variance in time. Okay, so I'm going to use the same notation as he did for a Gaussian process, you know, and think of this as the variance in time. So let me call this Wx. Okay, so this is saying that so S of t on so that now maybe, you know, my lack of an n in the notation for S is a bit of a shame, but this process depends on n here. So on n to the third is looking like cx minus x squared on 2 plus wx, you know, for so wx x at least 0, just a standard Brownian motion. So you can make sense of that as a statement about the whole process, but if you just want to think about it at a fixed time and not about the whole process, then you can just think of this as being a Gaussian, a centered Gaussian with variance x. Okay. So this whole story can be made perfectly rigorous. I mean, it's not far from being rigorous, except there's just some approximations that need justification. Okay. There's a question: what happened to the minus t for our approximation of st? So, so this binomial had a t, and had one of the terms that we worked out in this binomial was a plus t, and so when we subtracted off that t, it just canceled, and everything else happily had an n to the third power that we could factor out. Okay, so I have some, I think now I'm going to get to a prepared slide because I have some pictures of what this ST actually looks like. So, well, really sort of simulations of this limiting process. You know, here I'm, I think I've taken, you see, if C is, I think my pictures are all in the case C is 0. Okay, so C is 0 means that P is just 1 over n, or 1 over n plus 0 over n to the 4/3, right? But so this process in general looks like some Brownian motion with a parabolic drift, I'm just focusing on the case where the linear term is 0. So you get so here's a simulation of a Brownian motion. Okay, so this is the starting point. Then we add this parabolic drift to it. That's this this sort of yellow process here, which you can see is sort of roughly looking like the red process, but it's getting more and more negative over time. Okay, and that gives us this W prime. Okay, and now, so this is the thing that this W prime process is roughly, you know, what we're saying that the process S of really on the time scale, so x n to the 2/3 divided by n to the 1/3 looks like. Okay, but now, so that picture is sort of what I justified on the last slide, but now it's worth remembering what S is really doing for us, right? S was an exploration process of a sequence of components. So each time S here hits a new running minimum, that means it's sort of finished exploring a component. Okay, so, you know, there's one here, there's one here, there's one here, then there's sort of some biggish component being explored there, and so on. Okay, and this negative drift is going to make those component explorations smaller and smaller. That sort of corresponds to the fact that as the exploration goes on, the graph gets more and more subcritical. Okay, so rather than always sort of drawing these lines over to say, you know, what was our past running minimum and where's the component, we can just subtract off the running minimum process, right? So that, or in other words, just plot the number of just plot the length of the active queue. So that's S plus the running minimum, or S, right? Yeah, S minus its running infimum, or S plus the number of components. And that's this blue drawing here in the limit. So W plus, I'm calling it, is W prime minus its running minimum. Okay, and that gives you some process that looks like this. Okay, and the heuristic then is that these, you know, the excursions of this process away from 0 should correspond to the component sizes in the random graph. So, you know, 24 years ago, David Aldous made that story rigorous and proved that if you look at this, so first, if you look at the process which tracks the active number of active vertices and apply this same rescaling, x n to the 2/3 in time and n to the 1/3 in space, you converge to this reflected Brownian motion, it's called, so with parabolic drift. So Brownian motion with drift minus its running minimum. Okay, so that's the first step. And then as a consequence of that, because we know that A is also telling us about component sizes, you know, as a corollary of that result, you can prove, or Aldous did prove, that if you look at the sort of parameter regime we're interested in, so this is Gn 1 on n plus C on n to the 4/3. Okay, then if we order the components in decreasing order of size, so then in fact, so that vector of sizes, so let me write that as n to the minus 2/3 times the size of Ci, I at least one, will converge in distribution precisely to what I'll call Li. And so these are just the lengths, so the ranked sequence of lengths of these excursions. So biggest excursion corresponds to the biggest component, second biggest excursion corresponds to the second biggest component, and so on. So these are the ranked sequence of excursion lengths. Of W plus. And now here, you know, it isn't obvious in my notation, but this W plus process, its definition depends on C, right? Because this parabolic drift, the shape of the parabola depended on C. Okay, so when C is large and negative, we're going to start off with quite a negative drift, and all of the components are typically, all of these excursions are going to be quite small. When C is large and positive, we're going to start off with quite a positive drift, and then we'll expect our process to start by doing one of these big kind of excursions like the one we just studied in the sort of C tends to plus infinity limit. Okay. I think you have a redundant absolute value on the left. Yes, thanks. Right. Okay. So, so the last bit of the story I'd like to tell you is that you can actually also use this perspective to understand the surpluses. So remember that these components need not be trees. They might be trees, they might have extra edges. But this whole story that we've told so far can also actually be extended to understand component surpluses. So let me tell you how that works. So okay, so the key point for that is that as you go along the exploration process, okay, when you're exploring a vertex VI, you have the active vertex, and then you have this, the vertex you're exploring, and then the set A of active vertices. Okay, and you might add edges from the, in the graph GNP, there might be edges from the current vertex to the active vertices. And we didn't take those into account so far as we were discussing. We were always interested in just the exploration of the unexplored part of the graph. Okay, but you can also pay attention to those, right? So and those are the potential surplus edges. So the potential surplus edges are precisely those from VT to elements of AT minus 1. So there's a little shift in index just because if you go back to the definition of the process, the vertex VT sort of got defined. It was sort of the first thing that happened in the induction, so it got an index which was one bigger. But it's actually an element, sort of the top element of AT minus 1. Okay, so I think that this point is most clearly understood by a sort of quick example. And so rather than trying to do that by hand, I pre-prepared some slides, but for that I need to stop sharing my screen and share from my computer. So I'll do that now. So let's see. Right. So is that coming through okay? Okay, good. One yes means everyone says yes. Right. So this is just a reminder of the way our depth first walk worked for a given component, right? We start from the smallest labeled vertex, explore its neighbors, and then we always choose the sort of highest priority vertex with the smallest label to explore next. So that'll be 5. Its neighbors are 2 and 9. We explore 2. We'll discover 3. When we discover 3, we don't explore anything new. 3 has a neighbor which is 10, but 10 was already discovered. It's already sitting there in the active queue waiting to be explored. So nothing new happens. The queue length goes down by 1. When we explore 9, likewise, it has neighbor 7, but that was already discovered, so nothing new is added to the active vertices, to the discovered vertices. 7 has nothing interesting going on. Now the current vertex is 10. We discover 8. It has 2 neighbors, 4 and 6. We explore 4. And when we explore 6, the walk will hit -1, right? So this is the process we've seen before, just applied to a single component. Okay, now the point is that this is really the tree we explored, right? There were these extra edges which didn't change the depth first Q process. And also, in fact, the edge between 4 and 6 could have been present. That also wouldn't have changed the depth first Q process. Okay, but let's just go through that picture again and think about all the places that we could have added extra edges without affecting the this depth first tree, the tree that is explored by the depth first Q process. Okay, so what are the set of graphs with a given depth first tree? Well, I'll call the edges that we can add permitted edges. Okay, so that's, well, we saw in this example that these two edges between 7 and 9 and 3 and 10 wouldn't change things. They'd be permitted, but what are the other ones? Let's go through the process. We explore the neighbors of 1. The Q then has length 3. Now these red edges from 5 to 7 or 10 to the other Q elements could be added or left out, and they don't change the process, right? Because any edge from the current vertex to the things already in the Q isn't going to change the exploration. Okay, so I've drawn those two dashed edges, and then I've also indicated those two edges by the 2 dots above the k equals 1 in the discrete exploration process on the right. Okay, so likewise, any edges from vertex 2 to 7, 9, and 10, the things in the Q and 2 is explored wouldn't change the depth first tree, and we can equivalently sort of represent those by these points under integer 2 on the depth first Q process S. Okay, and so on and so forth. So at any given time, the set of permitted edges, the set of edges we could add without changing the tree, precisely correspond to the integer points under the process S at that time. Okay, so in this case, one of them was present. The edge from 3 to 10 was present in our graph. So let's just record that by putting a mark under the graph at this location 3, 0. Okay, I put it at 0 because 10 was the lowest priority vertex at that time. Okay. Likewise, so there was an edge from 9 to 7. So we'll put a mark at time 4 because we explored 9 at time 4, and it'll be the upper mark because 7 is the higher priority vertex. Okay. Likewise, there's one possible surplus edge we could add without changing the tree from 7 to 10. Nothing at time 10. The edge from 4 to 6 corresponds to this last lattice point under the curve at time 8, and nothing, no allowable surplus edges at step 6. Okay, so if that process, if you followed that description, then you should see that the edges you can add to this tree without changing the depth first tree precisely correspond to the lattice points under the excursion SK, so under the depth first Q process. Okay, so that means that if the graph has m vertices, we can figure out that number of permitted edges just by summing the height of the active Q, summing A of k over the steps of the exploration. Okay, so that's quite a nice connection. It says that in the limit. Now I'd like to stop sharing this screen and go back to sharing my iPad screen. So in the limit, this says that this process of this process is not just encoding the queue length and then therefore the sort of size of the component. It's also telling us about how many possibilities there were for surplus edges as we went along, right? And the number of possibilities is precisely proportional to the area under one of these excursions. Okay. So there's a question from the chat. So are there the size of AT or ST permitted edges? So in general, there's the size of AT, but because I only looked at one connected component, so if there are several connected components, then you have to use AT. But because I only looked at one, the two processes are equivalent. That kappa, there's no difference until until the two processes start diverging. Thanks for the question. Right. So these areas under these excursions are telling us about the number of possibilities for surplus edges. And of course, in the binomial random graph, each of those edges will, independently be present with probability P. Okay, so that tells us that if we look at a component that's explored from some time L to time R, conditionally given the active queue, so conditionally given the process, so AT for T from L to R, then the surplus will be binomially distributed with parameters. So the sum T from L to R, AT, P. Okay, and so if we're willing to sort of use the Poisson approximation to the binomial, this is saying that that number of surplus edges is approximately Poisson sum of AT, P distributed. Okay. The reason it's nice to use this Poisson approximation to the binomial now is because if we remind ourselves of the scaling for this process A, you see these excursions were having lengths of order n to the 2/3 and heights of order n to the 1/3. Okay. So that means this total discrete area under them is sort of random of order n. And so when the probabilities of order 1/n, then we're expecting to see sort of a Poisson with constant mean number of surplus edges. Okay, so that this was also part of the story developed by David Aldous. So if we list the excursions of the limit of W pros in decreasing order of length as, so let's say Wi plus I at least 1, and then write, so Wi plus so as Wi plus T for T between 0 and the length of the excursion. Okay, so what this is doing is saying, take this picture, right? Cut it up into individual excursions. So this would be the W1 excursion. It sort of has its time 0 here, and then it looks like this, right? And this is the W2 excursion, whatever. Should it be a yeah, someone pointed at a typo in the chat. Thank you. That should be times P. So if we list the excursions in decreasing order of length, okay, then jointly with the convergence of the component sizes, so jointly with the convergence n to the minus 2/3 size of Ci, again, don't need that, converging in distribution to the lengths Li, if we also want to study the surpluses of those components, I wrote S sometimes and surplus sometimes, but I'll write just surplus right now. The vector of surpluses of those components converges in distribution to some limiting surpluses, if you like, Si, I at least one. Okay, where, so remember in the discrete case, this was this discrete area, and in the continuous case, we exactly get a continuous area. So Si is Poisson distributed with parameter, the integral from 0 to Li of Wi plus T dt. So it's the area, it's Poisson with mean the area under the excursion. Okay. And so that tells us that the largest components of G of a critical random graph in this range, so they're random graphs, well, they're connected by definition. So their size is, you know, of order n to the 2/3 in probability. And they have surplus random, but of order 1 in probability. Okay. And so this really puts us back in the regime of the graphs we studied in the first part of the course, right? Because we saw that if you fix a large random graph with so large number of vertices and a fixed surplus, then we actually know how to build one of those distributionally. You start by some random drawing of some 3 regular kernel with random edge lengths. Right, and then you can use the sort of stick breaking construction to decorate that with a bunch of pendant trees hanging off of it. Okay, so when I say random connective graph, I mean uniformly random. I really mean uniformly random conditioned on the vertex set. So if I tell you, there's sort of enough symmetry in the problem that if I tell you what the set of vertices of the largest component is, and I tell you how many surplus edges it has, then it's equally likely to be any graph with that vertex set and that surplus. Okay. Right. So in particular, this tells us the largest connected components then will have sort of diameter of order n to the 1/3. So this is a statement I haven't quite justified to you, but we saw that for trees and graphs of this form, the lengths, at least the lengths of these sticks, the lengths of these paths and the lengths of these sticks were all of order square root of the number of vertices. So here, when the number of vertices is n to the 2/3, then the lengths of these sticks and paths will be of order n to the 1/3. Yeah, so that, this is a trivial comment, but the point is that this is square root of the number of vertices, square root of n to the 2/3. The question in the chat, it seems that in the scaling for the surplus, the C over n to the 4/3 term disappears. Yeah, that's a reasonable question. So the point is that here, so we're expecting this to be, something of order n, because these excursions were sort of random and had height. Where was it? Right, so these lengths are sort of random of order n to the 2/3, the heights are random of order n to the 1/3, so the overall area is random of order n, okay? And so then when we multiply by 1 over n plus constant over n to the 4/3, we're getting, order 1 in probability from the first term, and then indeed a vanishing correction as n becomes large. So that's so there is this correction to the probability affects the component sizes. It makes bigger components when C is large and positive, and smaller components when C is large and negative. But once you and larger components will indeed create larger areas for these discrete explorations. But that's the only way the factor C comes in. Once you know that area, then the correction to the probability really is vanishing for the number of surplus edges. Okay, I think that's a good point to wrap things up.